Okay, so before we do an example, I want to prove the most basic statement that those A and B in the definition of differentiability, we'll take a look at it again in a second, are none other than the partial derivatives. So that's this first theorem. So theorem, if fxy is differentiable at a point, x0, y0, then it has partial derivatives, sometimes called among buddies partials. Okay, the partials are partial derivatives at that point, and they're not just any mysterious things that exist, but they're precisely A in the definition is the partial derivative with respect to x, and B in that definition is the partial derivative with respect to y. Okay, so I want to prove this. By the way, okay, let's look at the definition just for a second here on this board. So remember, we have these A and B, and I want to prove that they're none other than the partials. Okay, but just a comment before we do that. This, of course, generalizes easily to more variables. So for example, if your function is a function of 3 variables, x, y, z, then it's going to be at the point x0, y0, z0, and you're going to have an a, b, and a c, and c is going to be the partial derivative with respect to z, and here you're going to have x0 plus h, y0 plus k, and then z0 plus j, and here you're going to have x0, y0, z0, and here you're going to have all 3 of them, and here it's going to be a function of 3 variables times h squared plus k squared plus j squared. Okay, so everything generalizes easily to more variables. Okay, just a comment. Okay, let's see now how this thing, which we called star for a single variable, but let's call it star again now. How does this yield that A and B are the partial derivatives? So remember that the partial derivative with respect to x kind of doesn't see what's going on with y, right? It's like freeze y, do everything only in the x direction. That's the idea of the partial derivative, okay? So that's what we're going to do. We're going to freeze y, and freezing y is just setting k to be 0. Do you agree? When k is fixed 0, then y throughout is just freezed. It's just y0. Do you agree? That's what we're going to do. We're going to take k to be 0 and write this entire thing where k is 0 and see what we get. Okay? So that's what I'm going to do now. So the proof of this theorem, take k equals 0 in star. Star is that expression that we had. So what do we get? We get, maybe let's move to this clean board here. We get f of x0 plus h, y0 plus k, but there's no k now, so y0, minus f at x0, y0, equals, I'm just rewriting star where k is 0, equals a times h plus b times k, but k is 0, right? Plus alpha of hk, but k is fixed, k is 0, right? So alpha of h0 times the root of h squared plus k squared, but k is 0. So it's the root of h squared. Do you agree? So plus alpha of h0 times h in absolute value, right? The root of h squared is h in absolute value. Do you agree? Okay, good. So this is what we get. Therefore, I'm going to divide throughout by h. So f of x0 plus h, y0, minus f at x0, y0 divided by h, what you should be seeing now is just the two-dimensional version of the proof of the fact that being differentiable in the single variable sense is equivalent to star in the single variable sense. That's what you should be seeing. I'm just doing the same thing. Once I'm phrasing the y variable, that's precisely what I'm doing. Do you see that? Okay. So minus, I'm going to write it minus, or let's do it in two steps, equals a, because I divided by h, plus alpha of h0 times, what's the absolute value of h? Let's leave it. Maybe I don't know, maybe we're going to need to assume h positive separately and h negative separately. I don't know, we'll see in a second. And now I'm going to move a to the other side. Okay, so, sorry, what I want to say now, as h goes to 0, what does this do? Becomes 0. Do you see that? Because absolute value of h divided by h is either 1 when h is positive or negative 1 when h is negative. Do you agree? So for positive h's, we're multiplying here by 1, and this thing goes to 0. That's the definition of alpha. Alpha of hk goes to 0 as hk go to 0, 0. Do you agree? So whether we're coming from the right or from the left, whether h is positive or negative, in any case, this thing goes to 0. Do you agree? So this portion, this expression, tends to 0 as h goes to 0. That's part of the assumption on alpha. Therefore, the limit, so this goes to 0. Therefore, if I take the limit as this goes to 0 on both sides, the limit of f at x0 plus h, y0, minus f at x0, y0, all of this divided by h, the limit of this thing as h goes to 0 is the limit of the right-hand side as h goes to 0, which is a plus 0, so it's just a. Do you agree? But what is this thing? This is precisely, by definition, the derivative of f with respect to x at the point. Do you remember? Good? So a is none other than the the x partial at the point. Okay, and likewise, if you freeze for b. So how do you prove that b is the derivative with respect to y? You freeze h as 0. Okay, that freezes x 0 and lets the y vary. Clear? Good? Everybody? Okay, so this proves this. And now let's do an example. Let's just do an example. Questions? Okay. So here's an example. I'm going to look at the function f of xy, which equals x squared y divided by x squared plus y squared to the power 1/2. That's like taking a root. That's whenever xy is not the origin. And 0 at the origin. So that's my two-variable scalar function. Okay, this is all the examples we've seen that have interesting phenomena going on were of this form, right? Because whenever a function, whenever I don't take kind of a case function like this and have something different happen at a point at least, then it's just going to be what did we call it? An elementary function, and the limits and the derivatives are all going to be calculated just by taking differentiation rules and plotting, taking the values, the limit at a point is just plotting the point into it, and everything becomes very easy and not interesting, okay? So whatever I'm going to say that's going to be interesting is probably going to happen at 0, 0, okay? Okay, so what I want to show that f is differentiable at 0, 0. That's what I want to show. How do I show something like this? Well, I have to show that that definition, which filled up an entire board, holds. That's being differentiable. Okay? And I have to check it by definition because we hardly have anything other than the definition at this point in time. Okay? The only thing we do have is that we know, we just proved it, that the a and b in the definition are going to be the partials, right? So in order to show that that definition holds, I have to show that the a and b exist, and the a and b better be the partials, so I better calculate the partials first. Okay? So the first thing I'm going to do is calculate df to dx at 0, 0, and df to dy at 0, 0, and those are going to be my a and b. Okay? So what is df to dx at 0, 0? So by definition, it's the limit as h goes to 0 of f at x0 plus h. But x0 is 0, right? So it's f at 0 plus h, comma 0, right? Let's do it in 2 steps. F at 0 plus h, 0, minus f at 0, 0, divided by h. Do you agree? That's just substituting zeros for x0 and for y0, because we're calculating at 0, 0. Okay? Now I want to plug in f. So it's the limit as h goes to 0. What is f at 0 plus h, 0? I have to take this expression, because it's not at 0, 0. It's at 0 plus h, 0, namely at h, 0. So I'm going to plug in h for x and 0 for y. So what do I get? I get 0. Do you agree? When x is 0 and y is, x is h but y is 0, this expression becomes 0. So I get 0 minus, this is 0 because it's this, 0, divided by h, and that's 0. Do you agree? Do you agree that similarly df to dy at 0, 0 is going to be 0? Okay, so df to dy at 0, 0 is also 0. Same calculation. So the conclusion by the previous theorem is that a equals b equals 0. The a is the partial with respect to x, the b is the partial with respect to y. Good? So I'm going to put 0 for a and 0 for b in that property that I called star and see if it holds. Okay, let's do that. Okay, so what was star? Star said take f at x0 plus h, f at x0 plus h, y0 plus k, minus f at x0, y0. That has to be equal, I'm trying to prove that this in fact holds. This has to be equal a times h, but a is 0, gone. B times k, but b is 0, also gone. But then there's the alpha component, alpha of hk times the root of h squared plus k squared. I have to show that this equality holds where alpha of hk tends to 0 as hk goes to 0. Do you agree that this is what I need to show? Need to show. We don't know this, we need to show this. We're trying to show that the function is differentiable. So we figured out what a has to be, we figured out what b has to be, and now we need to show that the property star holds. Do you agree? Everybody? Okay, so what do I need to show here? I have to say this is going to hold if I can find a function alpha of hk such that it satisfies two things. One, if I plug it in here, I get an equality. And two, it goes to 0 as hk goes to 0, 0. Do you agree? Everybody? So I need to find a function alpha of two variables, some mysterious function of two variables that satisfies two things. One, plug it in here, you get an equality. Two, it goes to 0 as hk goes to 0, 0. Do you agree? It's easy to guess what the function alpha has to be. Can anybody tell me what the function alpha is going to be? The only possible candidate that has a chance of doing this. Anybody? In fact, it's looking at you. Okay, you're not supposed to guess anything. Exactly. If alpha is going to satisfy this, if this is going to be an equality for any h and k, right, then just take alpha to be this divided by the root of h squared plus k squared. Do you agree? If those things are going to equal, then that has to be alpha. Do you agree? So define alpha of hk to be f at x0 plus h. I forgot one thing. Okay, we're not working with a general f here, right? F is concrete, right? F is the function we're considering. And we're not working with a general x0 and a general y0. We're looking at the point 0, 0. So let's rewrite this before I tell you what alpha is. Okay. So we need to show, so what is f at, so x0 and y0 are both 0, and f was given. So I'm going to write that. We need to show that. So I'm looking at the value of f at hk, because both x0 and y0 are 0. That's the point we're looking at. So what's the value of f at hk? H squared k divided by h squared plus k squared root. That's f at hk. Do you agree? Minus f at 0, 0, which was just 0. Right? And this has to be equal alpha of hk times the root of h squared plus k squared. This is what we need to show. Need to show. This was kind of abstract, but this is not an abstract example. This is a very concrete example. This is the value of f, where x0 and y0 are both 0. That's what we're looking at. Do you agree? Everybody? Okay. Define, now I'm going to tell you what alpha is. Alpha of hk, I'm going to take it to be this divided by that root. So alpha of hk is going to be h squared k divided by h squared plus k squared root, and again divided by that root. So it's just h squared plus k squared. Do you agree? Do you agree that this function alpha, if you plug it in here, you get an equality for every h and every k? Clear? So this is not a big guessing game. What we need to show now is that this thing goes to 0 as h and k goes to 0. Then it actually satisfies this property in the definition of being differentiable. Do you agree? Okay. So how do we show that? So it remains to verify, if we want to claim that this function is differentiable, that alpha of hk that we just defined goes to 0. Do you agree? Okay. How do I check that a function goes to 0. Remember, it's a limit in two variables. Okay? How do I do it? What are the tools that I have? By the way, where is this function defined?
0, 0.
Right, it's not defined at 0, 0. Do you agree? This is not defined at 0, 0. Is that an issue?
No.
It's not an issue because what we're checking is the limit of this function as we approach 0, 0. So the definition of the function at the point 0, 0, we don't care about. Okay? So we can, if both h and k are 0, this difference is going to be 0, and you can just take alpha hk to be 0. Okay? Okay. How do we calculate limits? Remember that what was the most handy tool to do such calculations? We remember we discussed it at quite a lot of length, what happens if we can show that limits don't exist as we come along different paths and so on and so forth. But what was the most useful tool for showing that a limit does exist? Hint at 0. Remember the r and theta business? Converting to polars? Remember? So that's what I'm going to do here. So what I want to show, I'm going to write h equals r cosine theta, k equals r sine theta, hope that it breaks up into some function just of r times some function just of theta, where the function in r tends to 0 and the function in theta is bounded. Remember that? Okay, so that's what I'm going to do. Let's erase here. So alpha of hk, which was h squared k divided by h squared plus k squared. So this equals, when I convert to r and theta, r squared cosine squared theta times r sine theta divided by r squared. Do you agree? Good? Does everybody remember what I'm talking about? What just happened? Why are you so quiet? Okay. So that equals, the r squared cancels. I get r times cosine squared times sine. This tends to 0 as r goes to 0. This is bounded in theta as a function of theta. And therefore, by the theorem that we had, the limit of alpha hk is 0 as hk approaches 0, 0. Good? So that's how you prove differentiability by definition. We're going to have other ways of proving differentiability using a certain theorem. Okay? Is it clear? Okay, I just verified the definition. I had to check what A and B are, and the theorem that we had that I just erased said, well, if it's differentiable, those A and B are not just going to be any numbers, they're going to be the partials. So I calculated the partials and checked if that property star holds. Let's look at it again. I checked if this property holds for the concrete f of the example and the concrete x0 and y0, which were zeros in the example. I isolated alpha, found out what alpha has to be in order to satisfy this equality, and then checked if it goes to 0. Clear? Okay, so it's a bit of work, but it's not terrible. Good, everybody? Questions? Yes?
Another way to prove that alpha tends to 0 could be...
Here.
Yeah. Could be to say that hk over h squared plus k squared is bounded, and then h tends to 0.
Okay, there are various ways of proving limits. Okay, you can use sandwich theorem sort of arguments. Was that what you were hinting at? Yes, that's fine. Any way you have that works is good. Okay. By the way, what would happen if you see that the limit doesn't exist, or the limit is not 0? What would that imply?
Not differentiable.
Right, that the function is not differentiable. And note that that could happen while still having partial derivatives. Okay, so having partial derivatives does not guarantee differentiability. You can't just calculate the partials and stop there. Okay, we've seen an example. We didn't have the notion of differentiability yet, but we've seen an example where a function had partial derivatives but didn't have a tangent plane, or didn't have a limit at 0. And the proof that that is a counterexample to this statement is that we're going to have a theorem that differentiability implies continuity. And in that example, we had partials, but it was not continuous. Therefore, it can't be differentiable. Okay? How many people just got totally confused by what I said? Okay. We'll discuss it in the next clip in a couple of minutes. Okay?